Let's take a look at this question over here. What does this question say? Based on complex numbers and quadratic equation miscellaneous exercise, this is question number 11, and the question is pretty simple. As you can see, that a plus ib is given to be equal to x plus I whole square over 2x square plus 1, and you are supposed to prove something else. Now, we have seen similar question related to like this before, and the important thing to observe over here, as you can clearly see, is this a plus ib and this a square plus b square is related in some way. Now, what is that relation? A square plus b square is nothing but the square of modulus for this complex number a plus ib. Yes. And what is happening in the right hand side is something similar. Yes. So, for proving this complete statement, let us begin with what is given. Given that it is given to us that a plus ib is equal to x plus I whole square over 2x square plus 1. This is given to us, right? Since this complex number is equal to this complex number, we can take modulus on both sides. Yes. Let us take modulus. Implies that a plus ib modulus is equal to modulus of this whole thing, which is x plus I whole square over 2x square plus 1. This is what we have, right? That's pretty simple, yes. Once we know this much, then we can continue further, and this modulus is equal to, let us write it for in the same manner once, right? And use properties of modulus on this. What you get is modulus of z1 upon modulus of z2 will be equal to mod z1 upon mod z2. Okay, so the denominator becomes 2x square plus 1 modulus. The numerator becomes modulus of this whole thing, and there is a square also involved. Modulus of z square would be equal to modulus of z complete whole square, and I can write it as modulus of x plus I whole square. That's simple, yes. Once we are through with this modulus of a plus ib can be written as this is equal to a square plus b square in the under root. This x plus I modulus is equal to under root of x square plus coefficient of, with this I, we have the imaginary part 1, that is 1 square over here. Okay, and then there is a whole square. Okay, what happens to this? This is 2x square plus 1. Modulus of this whole thing will be simply 2x square plus 1. This one's only real part, right? It does not have any imaginary part. And this is a positive quantity, as you can clearly see over here. 2x square would be greater than equal to 0 for x real, right? Okay, what next? What next? So now we can square both sides and we can get a square plus b square is equal to, this is actually x square plus 1, under root square would be actually x square plus 1 only, and on squaring you will get x square plus 1 whole square. Whole divided by this is 2x square plus 1, and again on squaring you get this. This is on squaring. And let us take a look at what was being asked. Let us take a look at this. So we were asked to prove a square plus b square is equal to x square plus 1 whole square and upon 2x square plus 1 whole square. And yes, we have done exactly that. This is a complete proof of this question over here. Let's talk about this question next. Let z1 equals 2 minus I, z2 is equal to minus 2 plus I, and we are supposed to find the two parts of this question. In the first part, we are supposed to find the real part of some expression depending on z1 and z2. And in the second part, we are supposed to find the imaginary part of some expression depending upon z1 and z1. z1 and z1 bar is there. Okay. How to go about attempting this question? It is pretty simple. First of all, instead of finding the real part directly, what we'll do is, we'll first simplify this expression over here. Let's take a look at this expression and try and solve the first part. So first thing that we are supposed to do is simplifying this expression. Let's take a look at the expression first. What do we have in the first part? We have z1, we have z2 and the conjugate of z1, that is z1 bar in the denominator. Okay. Let's write z1. z1 is 2 minus I, z2 is minus 2 plus I, and the conjugate of z1 would be z1 bar, which is actually 2 plus I. This is 2 plus I over, right? Let's simplify this. Okay. Well, multiply these two terms in the numerator. What you get is 2 times 2. Okay. Or as you can clearly observe, okay, let's multiply them together. You can also observe that this is negative of this actually, right? You take a minus common and what you get is a 2 minus I. This is already a 2 minus I. So this is actually 2 minus I times 2 minus I. I can move in that direction, or I can directly multiply by using the distributive law. That is 2 times minus 2 would be minus 4. 2 times I would be 2I. Minus I and minus 2 multiplied together would give me plus 2I. And minus I plus I would be minus I square in the numerator. The denominator is 2 plus I, which is not difficult to handle. We'll multiply with 2 minus I over here and 2 minus I over here. The complex conjugate of this 2 plus I in the LHS, on the right hand side as it is, right? That's what we have, okay? So on getting this expression, what do we get is, let's take a look at this. This is minus 4 and this becomes minus of minus 1, which is plus 1. So minus 4 plus 1 would be minus 3 plus 4I in the numerator, the first term. The second term would be 2 minus I, as you can observe over there. In the denominator, you get a plus b, a minus b, which will be a square minus b square. That is 2 square, 4 minus I square. That's what you will be getting, right? Okay, let's simplify this further. By multiplying the numerator, what you get is minus 6. Those minus 3 times 2 is minus 6. Minus 3 times minus I is plus 3I. 4I times 2 is 8I. And 4I times minus I is minus 4I square in the numerator. In the denominator, you get a I square is simply minus 1. So this becomes 4 plus 1 over here. Okay, what next? Let's continue further and simplify it more. This further becomes equal to, this is minus 4I square, which becomes minus 4 into minus 1. That's plus 4 minus 6. Okay, plus 4 minus 6 would be actually minus 2. This is 8 plus 3, which is 11I whole divided by, you have a 5. And this gives me minus 2 by 5 plus 11 by 5I. This is the expression that Z1, Z2 over Z1 bar. That expression is equal to this. Therefore, real part of Z1, Z2 over Z1 bar is actually equal to what? Real part of this whole thing, as you can observe, that is simply minus 2 by 5. And yes, that is my answer for this question over here. This is first part for us of this question. Let's try and take a look at the second part. Now, second part once again is not very difficult to handle. What you have over here is Z1, Z1 bar in the denominator. Now, one of the ideas is to simplify Z1, write Z1 bar and then multiply them together. Or another approach would be, what you need in the second part is 1 over Z1 bar. Now, what is that equal to? ZZ bar, as you may recall, ZZ bar is actually equal to mod Z square. What we know is Z bar is equal to mod Z square. This is something which we know. So this is mod Z1 square in the denominator, right? That's what we have. And modulus of something is actually only a real number. That's what we know, right? So what do we get over here is something very simple. What you get over here is actually Z for Z1. This is 4 plus 1, which is 1 over 5. This is this whole thing. And what's the imaginary part in this case? I can write it as 0I. Therefore, imaginary part of 1 upon Z1 bar is simply equal to 0. That's what I can observe over here very easily. And yes, this is the final answer for this question over here. Let's move on to the next one after this. What does this question say? Find the modulus and argument of the complex number this. 1 plus 2i over 1 minus 3i. Now, how are we supposed to find the modulus and argument? For finding the modulus and argument, first we need to convert in the standard form. That is a plus bi form, right? So for that, let's simplify this complex number, okay? So let z equals 1 plus 2i over 1 minus 3i. Now, for simplifying this, we'll have to multiply with the complex conjugate of denominator, right? 1 plus 2i over 1 minus 3i times 1 plus 3i over 1 plus 3i. Now 1 plus 3i is the complex conjugate of this denominator over here, and we multiplied it with this. In the numerator, let's apply the distributive law and we get 1 times 1, which is 1, plus 3i. 2i times 1 is 2i, and 2i times 3i is actually 6i square. So this is 6i square in the numerator. What do you get in the denominator? Let's take a look at the denominator. This is a minus b, this is a plus b, this is a square minus 3i whole square, which is 9i square. This is what I get, right? Let's continue further and see what do we get further is this 6i square becomes equal to what? This 6 times i square is actually minus 6. 1 minus 6 will become equal to minus 5, okay? This 3i plus 2i is actually equal to 5i. Whole divided by, what do we have over here is 1, I square becomes minus, so this becomes plus 9, 1 plus 9 is actually 10 in the denominator. Okay, this is what I am getting. Further, what next? This is minus 5 by 10, which is minus 1 by 2, plus 5 by 10, which is 1 by 2i. This is my complex number z. And now I am supposed to find the modulus and argument of this complex number. Finding the modulus is not very difficult. Modulus is very simple. Therefore, modulus of z is equal to minus half square, which is 1 by 4. Half square, which is 1 by 4, and we take the under root. This is under root of x square plus y square. What do we get over here is this 1 by 2 in the under root, which gives me 1 by root 2. Right? This is what you get. Modulus of z is very simple. For finding the argument, what are we supposed to do? For finding the argument, we are supposed to plot the point in the argand plane first. Let's plot the point in the argand plane. This is minus half comma half. This is minus half over here and half over here. The point lies in this quadrant over here, right? And the argument would be actually this angle. The argument would be actually this angle theta over here. Theta is the argument. In that case, let's try to find theta somehow. How will we find theta? This is half, this is also half, and we can find this alpha very easily, right? Tan alpha, as you can clearly observe, is 1 by 2 upon 1 by 2 in this right angle triangle over here. This is 1 by 2 upon 1 by 2, which is 1, giving me alpha equals pi by 4. Now, once you get the value of alpha, therefore, you can easily find the value of theta. Therefore, theta, which is argument of z, is actually equal to, from here to here, it is pi, and we'll have to subtract pi by 4 from pi, thereby giving us argument as 3 pi by 4. The argument of this complex number z is 3 pi by 4. The modulus is 1 over root 2, as you can observe over here. The argument is 3 pi by 4, as you can clearly observe over here. And is that all? Yes, that is all in this question over here. Next, let us talk about the next question, that is this. How do we solve this question? Find the real numbers x and y if this whole complicated expression is the conjugate of this complex number. Okay, that's what the question says. So let's take a look at this question. And real numbers x and y are real numbers, and this is the conjugate of this. Okay, so let z equals minus 6 minus 24i. Okay, this is a complex number given, and this whole thing is a conjugate of this. Therefore, and z bar is equal to, since conjugate of this is this, x minus iy times 3 plus 5i. This is given to me, right? This is given to me, yes. Z bar equals to this. This is also given. This is also given. Right. So therefore, I can say that z bar, for this z bar can easily be found as minus 4 minus 6 plus 24i. This is the actual conjugate of this, which I can directly see from here. And this is equal to this x minus iy times 3 plus 5i. I hope that's okay. Yes, that's pretty simple. And on rearranging this expression, what I get is x minus iy will be actually equal to what? Divide with 3 plus 5i. Minus 6 plus 24i over 3 plus 5i. This is equal to this. Now that complex number over here on the LHS has real term, real part x and the imaginary part minus y, and on simplification, on simplifying this in the form a plus ib, will get the values of x and y very easily. So the next task that we are supposed to follow is simplifying this expression. And how do we do that? We'll have to multiply with the complex conjugate of denominator 3 minus 5i in the numerator and in the denominator as well. Let's multiply this. Therefore, x minus iy becomes equal to what? These two terms will get multiplied. Let's apply the distributive law. This minus 6 gets multiplied by 3, which gives me minus 18. Minus 6 gets multiplied with minus 5i, which gives me plus 30i. Okay. 24i gets multiplied with 3, which gives me 72i. And 24i gets multiplied with minus 5i, which gives me minus 120i square. And what about the denominator? In the denominator, you have a plus b and a minus b, which will be a square minus b square, which is 25i ka whole square. What next? This is minus 120i square, minus 120i square. I square is minus 1. That will give us plus 120 over here. Plus 120 minus 18 is plus 102. That's what I get, right? Plus 102. What about the second term? This is 72 plus 30, which is plus 102i in the numerator, as you can observe, right? What about the denominator? In the denominator, you have 25i square. I square is minus 1. This becomes plus 25. Plus 25 plus 9 is 34 actually. 34 in the denominator. Can you observe that? Yes. This is 34 in the denominator. And on observing this, what next? 34 times 3. This is 3 plus 3i over here. Right? This is 3 plus 3i over here. And yes, this is equal to x minus I y. On comparison of the real parts, we get x equals 3 and minus y equals 3, which gives me y equals minus 3. So x is simply equal to 3 and y is equal to minus 3. This is obtained by comparing the real parts, and this is obtained by comparing the imaginary parts of LHS and RHS, since the two complex numbers are equal. And yes, that is all for this question over here, as you can see completely, right? Let's move further and talk about this one. 15th, find the modulus of this expression over here, this complex number. Okay, if you are supposed to find the modulus, we'll have to simplify first, right? Since the complex numbers are in addition and subtraction, a lot of things are happening over here. They're not in multiplication and division. Had they been only in multiplication and division, we could have applied properties of modulus. But here we cannot apply properties of modulus directly. What we'll have to do is we'll have to simplify first. For finding the modulus, let us take it as z equals 1 plus I over 1 minus I minus 1 minus I over 1 plus I. Simplifying this separately and this separately does not seem a good idea, because on taking the LCM, you get conjugates getting multiplied together, right? Had they not been conjugates, we would have thought in another direction, maybe. But right now, we can move directly by taking the LCM. What do I have here is my 1 minus I times 1 plus I in the denominator. This is the LCM, and is it actually LCM? No, it is not actually LCM. It is way of simplifying, that is adding these fraction terms, right? Okay. Now, what is LCM, you may ask? LCM is actually a multiple. Now, when we talk about multiples should be in terms of, let us say, natural number products, right? Products with natural numbers. But here, we are simply multiplying these two together, and in that case, for simplifying, what do we get over here in the numerator is 1 plus I whole square minus 1 minus I whole square, right? So we are adding these two fractions, and this is how we do it. Okay. Next, what do we get? This 1 plus I square and this 1 minus I square is actually a square minus b square. Can you observe that? Yes. So a square minus b square can be written as a plus b, which is 1 plus I plus 1 minus I. This is a plus b. There's another bracket which says a minus b, that is 1 plus I minus this minus 1 and minus of minus becomes plus I over here. This is what I get, right? This is what I'll be getting. What about the denominator? This is a minus b, a plus b, which is a square minus b square. This is what I'll get. Right. What's the first term in the numerator? Can you observe that the i's get cancelled? This becomes 2. What about this expression? The 1 get cancelled and this becomes 2i. Okay. What happens to the numerator? Sorry, to the denominator. In the denominator, you have an I square which is equal to minus 1. 1 minus minus 1 and product that will be equal to 1 plus 1, which is 2. Okay. And so this complex number is actually equal to 2i. That complicated expression simplifies to this 2i, and since z equals 2i implies modulus of z equals 2, and yes, that is my answer for this question over here, right? Is that all? Yes, that is all in this question. Let us take a look at this one. If x plus iy whole power 3 is equal to u plus iv, then show that this expression equals this expression. Okay. Now, how do we go about approaching this one? If we take a look at ux, vy, this u and v are, let us say, in products and in addition subtraction with these x and y terms on the LHS, present in the LHS in the given expression, right? Since they are intertwined, we cannot solve this separately and this separately as we had done for a past few questions, right? We had taken modulus and simplified them together. So such an approach is not possible over here. What do we do? What we'll do is we'll try to find u and v first then, right? And that is what we'll begin with. Given that u plus iv is equal to x plus iy whole power 3 implies this is equal to what? X plus iy power 3 can be further written as this is a plus b whole cube, which becomes a cube plus 3a square b, which is iy, plus 3a b square, which is iy square, which is I square y square, plus b cube, which is I cube y cube. This is what we have, right? Can we simplify this further? Yes. This I square is actually equal to minus 1. Okay. So this becomes minus 3xy square. Okay. There's an x cube over here. So x cube minus 3xy square is actually the real part, right? What happens in what happens in case of imaginary part? What you get is, let's take a I common. This becomes 3x square y. And what happens to this term over here? There's an I cube over there. And what can we say about I cube? I cube is actually I square times I. I square is minus 1, yes. So this is minus y cube. I is already taken out common. This becomes minus y cube over here, right? Okay, so therefore u plus iv is actually equal to this. And on comparison of real parts and imaginary parts, which we get u equals x cube minus 3xy square, and v is equal to, real part becomes equal to real part, v is equal to 3x square y minus y cube. This is what we have. The imaginary part is equal to imaginary part. Now always keep an eye on what is to be proved. We are supposed to prove u upon x, v upon v. You observe that u and v are only present at one locations, and therefore we have found the values of u and v. Now what next? We are supposed to find u upon x actually. Let's try to find u upon x. Can you divide by x on the LHS and right hand side? Yes. Dividing by x, this becomes x square and this becomes 3y square. Okay, minus. And v over y is something else that is required, and v over y is equal to, let's divide with y, this becomes 3x square minus y square. Can you observe that? Yes. The question is asked in such a manner that your calculations become very simple gradually as you move ahead. And now u over x plus v over y is equal to what? U over x plus v over y is equal to this plus this. Let's add them together. What you have is x square minus 3y square plus 3x square minus y square. This is equal to 4x square minus 4y square, which is actually 4 times x square minus y square. That means u over x plus v over y is actually equal to this. And yes, this is the exact same thing that we were asked to prove. That is the complete proof of this particular question, right? It's a complete proof. Yes, that is the complete proof, as you can see over here. And that is all in this question, as you can see. Next, let us take a look at this. If alpha and beta are different complex numbers with modulus of beta equals 1, then find the modulus of this expression, right? The modulus of beta minus alpha over 1 minus alpha bar beta. Okay. Now, how do we approach this question? As you can observe, there are two complex numbers involved over here. And when you go about thinking how to approach this question, you would find that your hands are tied, pretty tied for that matter. Okay, how to get free from that tightness? What is the problem in this particular question? Alpha and beta are different complex numbers. Okay, so alpha is not equal to beta and both are complex numbers. Okay, with magnitude, modulus of beta is actually equal to 1. This is given, modulus of beta equals to 1. Okay, both of these are given. Okay, we are supposed to find beta minus alpha over 1 minus alpha bar beta modulus, and this is supposed to be found, right? As you can clearly observe, there's not much information given about alpha in the given question. Only a little bit of information is given about beta, that its magnitude is 1, its modulus is 1, and we are supposed to find this complicated expression somehow. How do we go about approaching this kind of a question, and this particular question in general? Let's talk about this one. So since there's not much information, there would be some manipulation and things would get simplified, right? What can we do with this expression over here? Let's try to use this expression somehow. Okay. So modulus of something actually is very limited knowledge, very limited properties are there of modulus, right? And one of the very important properties of modulus, you may recall, is mod z square is actually equal to z bar. This is one very important property of modulus where we can use z and z bar, right? I'll use this property first. So modulus of beta minus alpha over 1 minus alpha bar beta. Let's try to find the square of this modulus. Okay. I'm trying to find the square of this, and how do we go about finding this? This is mod z square is actually equal to z times z bar. That is, this complex number mod square would be actually equal to this complex number times its conjugate. So what do we have is beta minus alpha over 1 minus alpha bar beta. And we have beta minus alpha over 1 minus alpha bar beta complete conjugate. That's what we have on the RHS. Right. Now that's actually Z1 upon Z2 bar type of a thing. And what happens in this case, this will become, the bar will go on the numerator and the denominator. What you get is Z1 bar over Z2 bar. Using property, the other property, I'm writing the property over here. Z1 over Z2 complete bar is actually equal to Z1 bar over Z2 bar. That's the property that I'll be using next. So what you have over here is beta minus alpha is okay. 1 minus alpha bar beta is also okay. And what you get over here is beta minus alpha complete bar over 1 minus alpha bar beta complete bar. This is what I get. Another property of conjugate. What's that? Z1 plus Z2 bar is actually equal to Z1 bar plus Z2 bar. Yes, this is what we know, right? So let's use that. Next, I'll use that. This is beta minus alpha, which is okay. This is beta bar minus alpha bar in the numerator. What happens in the denominator is, I already have a 1 minus alpha bar beta. And what does this become? This is 1 bar, which is actually equal to 1 only, minus alpha bar bar. Okay, alpha bar beta whole bar would be actually equal to alpha bar bar. That is conjugate of alpha, which is actually alpha only. And beta conjugate would be actually equal to beta bar. This is what I'll be getting. Right. Now, as you may observe, we can simplify these expressions, right? Let's multiply them together. And what do we get? On multiplying beta and beta bar, we get beta bar minus beta alpha bar. That is, let's write it as alpha bar beta, right? I'm multiplying this beta with this beta bar, applying the distributive law. Beta times alpha bar is this, alpha times beta bar minus alpha beta bar. What next? Minus alpha and minus alpha bar. What is that equal to? That's equal to plus alpha bar. That's equal to this, right? What happens in the denominator? In the denominator, you have 1 times 1, which is 1. 1 times alpha beta bar. This is what you have. Minus alpha bar beta in the denominator. And the last term would be minus alpha bar beta minus alpha beta bar. That will be actually equal to plus alpha bar beta bar. Now recall, there was one more condition which was given, and that condition was only on beta. Modulus of beta is equal to 1. And since modulus of beta is equal to 1, we know that, I'll use another idea over here. Beta bar is actually equal to modulus of beta whole square, which is equal to 1. And yes, that is something I'll be using next, that beta bar is actually equal to 1. So this becomes 1 minus alpha bar beta minus alpha beta bar plus this is, what is this? Alpha bar is actually, alpha bar would be actually equal to, what do we have? Alpha bar would be actually equal to mod alpha square. So this is mod alpha square over, what do we have over here is, observe, this is a 1. Then there is a alpha beta bar. Okay, let's write it as over here. There's alpha bar beta, let's write it over here. Okay, those are the two terms. What about the last term? You have a alpha bar, which is mod alpha square. What about beta bar? Beta bar is mod beta square, which is equal to 1, and this is what I get. Since beta bar is equal to mod beta square is equal to 1. That's what we have in the bracket over here. Since this is it. And what do you get over here? Do you observe that this numerator is exactly same as this denominator over here? Yes. If you can observe that, we say that these get cancelled, and what you get is this is equal to 1. So modulus square is equal to 1. What will modulus be equal to? Therefore, this modulus is equal to 1 and minus 1. No. Modulus is positive, right? So it is equal to plus 1. And yes, that is my answer for this question over here. That's the analysis behind that. And that's the important step behind all of these things. Because this modulus is pretty difficult to find. But with this idea, the very important property of modulus, the most important property of modulus, this modulus of z square is equal to z bar. And on the basis of this, you have solved this question, right? That is all? Yes, that is all in this question. Let's take a look at this one. Find the number of non-zero integral solutions of the equation. Non-zero integral solutions is what we are looking forward to, right? And number of non-zero integral solutions is what we are looking forward to. So let's take a look at this. What we have is modulus of 1 minus I power x is equal to 2 power x. Okay. Now modulus of 1 minus I is not difficult. We can easily find that. What you get is root of 1 plus 1. 1 square minus 1 square, and power x is equal to 2 power x. Where does that take us? This is root of 2 power x. Pretty interesting. This is 2 power x. Okay. This actually gives me 2 power x by 2 is equal to 2 power x. And since 2 power x or 2 power t is increasing function, right? It's an increasing function. Exponential is increasing continuously. It is a monotonic function. Therefore, x by 2 will be equal to x. X by 2 would be equal to x. Okay. From here, we can directly reach this point, and on the basis of this, you can observe that x equals 2x, or you can say that x equals 0. Now, that is a solution that I am getting, right? How many solutions? So, the person has asked the number of, mind you, non-zero integral solutions. So, is this an integral solution? Yes. But is it non-zero? No, this is not non-zero. It is 0, right? The solution, the final value that I am getting is actually 0. And that is the only possible solution. But since the person has asked non-zero integral solution, so then is there any non-zero integral solution available? No non-zero integral solution exists. There is no such non-zero integral solution. Therefore, number of non-zero integral solutions would be actually 0. That is my final answer for this question. Number of non-zero integral solutions is 0. That is my answer for this question over here for this equation, right? And that's what you can take a look at once again. Let's take a look at this question. If A plus IB times C plus ID times E plus IF times G plus IH is equal to capital A plus I capital B. Okay. The product of these four complex numbers is equal to another complex number, then show that. This product multiplied with this, multiplied with this, multiplied with this becomes equal to this. And yes, how do we go about approaching this question? We have been doing this kind of a question, right? This A plus I, B and A square, B square seem to, A square plus B square seem to be related among themselves. And yes, this expression is nothing but modulus of this square, right? And this is true for each and every one of this. So what we'll do is, we'll begin with what is given. Given that A plus IB times C plus ID times E plus IF times G plus IH is equal to A plus IB. We'll begin with this. And what we'll do is, we'll take modulus both sides. Let's take modulus both sides. Now, on taking modulus, what I get is, this is modulus of Z1, Z2, Z3, Z4, and which will be equal to mod Z1, mod Z2, mod Z3, mod Z4. That is mod of A plus IB, mod C plus ID, mod E plus IF, and mod G plus IH, which is equal to mod A plus IB on the right hand side. Okay. And now find the modulus of this. That is, modulus of this would be under root of A square plus B square, under root of C square plus D square, under root of E plus square plus F square. This is under root of G square plus H square, which is equal to, on the right hand side, you have again under root of A square plus B square. What next? A simple step, one more. Square. Let's square both sides. The LHS and RHS would still be equal on squaring. What you get is A square plus B square, C square plus D square, E square plus F square, G square plus H square is equal to A square plus B square. And that's all, right? That's the proof. That's the final expression that was asked. That was required. That is the final expression. Yes. Is that all? Yes. That is all in this question, as you can observe over here. Let's take a look at this one. 20th. If 1 plus I over 1 minus I whole power m is equal to 1, then find the least positive integral value of m. Very interesting. Least positive integral value of m. These terms are very important. These expressions, what do you call? Least positive integral value. So you're talking about integral, you're talking about positive integers. So what you're talking about is actually natural numbers. That is 1, 2, 3, 4, right? And you need the least possible value of this. Okay. So let's try to find the solutions of this first in terms of natural numbers. In this set of natural numbers. Let's try to find the solution of this equation. 1 plus I over 1 minus I whole power m is equal to 1. How do we go about solving this? We'll have to simplify this one first, right? What is this expression actually equal to? Let's try to simplify this first. What you get is something power m is actually equal to 1. But something can be simplified as 1 plus I over 1 minus I. Let's multiply with the complex conjugate of this denominator. Let's try to bring this complex number in the numerator. And what you have is 1 plus I whole square in the numerator over here. This is a minus b, a plus b, which is a square, and minus of I square. What minus of I square would actually become plus 1 over here in the denominator, right? And this power m is equal to 1. This is given as power m is equal to 1. What does this simplify into? Let's take a look at this. 1 plus I square is actually equal to a square plus b square. Now, b square is I square, which will be equal to minus 1 plus 2 times I, 2 times ab. What you have in the denominator is 2. And this whole expression, power m, is given to be equal to 1. Okay. This is cancelled. 2i upon 2 is actually I. I power m is equal to 1. Okay. So that expression, that complicated expression is actually equal to simply I. That 1 plus I over 1 minus I is simply equal to I only. Yes. And I power m equal to 1 can have many solutions. Right. We remember that I is square root of minus 1. I square is equal to minus 1 and I power 4 is actually equal to 1. And on the basis of this, we can say that any multiple of 4 power, that is I power 4k, is actually equal to 1, where k can be any integer, right? So any multiple of 4 is okay. Therefore, m can be equal to what? M can be equal to 4, 8, 12. Now these are positive integral solutions, mind you, positive integral solutions. We could have had other solutions as well. We could have 0, we could have had minus 4, minus 8, minus 12 as well, but these are not being asked right now. We are only asked to find a positive integral, and out of those positive integral solutions, we are supposed to find the least positive integral solution. That is, the least positive integral solution, as you can observe, is 4. Therefore, least positive integral solution m is equal to 4 is my final answer over here. Possible values of m, as you can see, can be many. Possible values of m, as you can see, can be many, right? This is background check. This is the final answer of this question over here. So simplifying this expression in the bracket was the important thing, as you can observe over here, right? Right. Yes. And that is all in this exercise. This is miscellaneous exercise of chapter 5, complex numbers and quadratic equation. That is all in this exercise.